Good morning. In the last class, we were discussing what happens in the universe at temperatures around 10 to the power 10 Kelvin. To get the picture clear, let me just briefly tell you the scenario at this temperature. At this temperature, the CMBR is sufficiently hot to excite the neutrinos. So, if there are different kinds of neutrinos, so the temperature of 10 to the power 10 Kelvin is sufficiently high to excite these neutrinos. It is also sufficiently high to excite the electron positron pairs. Okay. So, you have these, let me just explain this. So, we have an electron and a positron. Now, these can combine to give rise to photons. Okay. Gamma ray. So, these give rise to photons. They can annihilate and give rise to photons. Okay. This all the charges are conserved in this process. This electric charge, electron number, etc., are conserved. Okay. So, you can have, this is called annihilation. So, the electron and positron can combine to give rise to photons. Now, electrons, the minimum mass that electrons can have is mc square. The minimum mass for photons is 0. Okay. So, if you want photons to produce electron positron pair, they must have energy. The photon energy should be greater than 2 mc square, m electron c square. So, if we have radiation at temperature kBT greater than or equal to mc square of this order, okay, it is only then that the radiation, the thermal radiation, can excite the electron and the positron pairs. If the temperature is much lower, then you will not be producing much electron and positron pairs. The reaction will proceed mainly, even if you start off with electron, positrons and photons in thermal equilibrium, and then you reduce the temperature. If you reach a temperature below m electron c square, then the reaction will proceed and towards this right hand side, and you will, all of them will annihilate. Okay. At temperature, when the temperature is more than the rest mass, then you will have copious number of electrons and positrons. Okay. So, if you have, so at temperatures more than the rest mass in thermal equilibrium, you will have copious number of electrons and positron pairs. Okay. And these will be described by a Fermi-Dirac distribution. That will be always so, but at temperatures below mc square, the number of the occupation number is going to be negligibly small. Okay. So, these numbers are much, okay, what we see now are the residual electrons. So, this annihilation occurred somewhere around 10 to the power 10 Kelvin. Okay. What we see now are the residual electrons after this annihilation is over. So, there was some excess electron, that is what we believe, which survived this annihilation. Okay. So, the chemical potential for this electrons is approximately 0, because the residual electrons that we see now, as we have seen, the ratio of that, okay, at these temperatures, let me just explain these at this point. At these temperatures, when they are in equilibrium, the number density of electron is comparable to the number density of photons, because this is in Fermi-Dirac distribution, this is Bose-Einstein distribution. Okay, we shall see that the number densities are comparable. At present, I have already estimated the ratio of baryon to photon, it is extremely small. The ratio of electron is similar, right, because we know that the universe is neutral. So, if those are number density of protons, the number density of electron is same. Okay. So, at present the electron number density is much less than the photon number density. So, we can say that after this annihilation process, the residual is negligible. It is actually a very small number that survives. Okay. So, the chemical potential for this electron, chemical potential for positron, sorry, other way around, this is positron, this is electron, this is equal to 0. Okay. So, the number density of electron and positron was the same when these numbers were copies, and it is the same afterwards also, approximately 0 now. Okay. So, we have this electron positron pairs being produced at temperatures higher than 10 to the 10 Kelvin. At these temperatures you also have the neutrinos, right. So, we have the electron, the topic of discussion today is going to be, we are continuing discussing the thermal history. Today we are going to concentrate on the neutrino background. Okay. So, we have these electron positrons at that temperature. We also have the neutrinos, and the neutrinos are in equilibrium with the cosmic microwave background radiation, which is in equilibrium with the electron positron pair. So, they are all in equilibrium, and through this. Okay. So, neutrinos and antineutrinos can ionize, can combine to produce electron and positron. Okay. There was another reaction which I had written down yesterday. This is also allowed. Okay. Then go over to photons. This, based on this, we said that the chemical potential for these two should be 0, because this has a 0 chemical potential. These two should be equal and opposite, and we had assumed them to be 0. There is also this reaction, and it is through this reaction that the neutrinos are in thermal equilibrium with the electron positron pairs, and the electron positrons are charged particles. So, they are obviously in thermal equilibrium with the photons. Okay. So, we have these neutrinos. So, we are discussing a situation where there are three kinds of things. There are neutrinos, and then there are electron positron pairs, and then there are these AMBR photons. All of them are in thermal equilibrium. Okay. At temperatures more than 10 to the 10 Kelvin. Then what happens is all in equilibrium. Then what happens is, with the expansion of the universe, the electron positron pair number density is falling, the photon number density is also falling. Okay. Now, these neutrinos only interact through the weak interaction, their scattering cross section is rather small. Okay. So, the chances of these neutrinos interacting is small. Okay. So, these reactions are significant at high temperatures, high densities, but as the universe expands, what happens is that these reactions go out of equilibrium. Okay. So, the neutrinos decouple. First, the neutrinos decouple. Okay. So, what do we mean by this? They stop reacting with the rest of the material. The universe is expanding, so the density and the temperature of this whole thing is falling. The reaction rates fall as the universe expands. So, at a certain temperature, around 10 to the power 10 Kelvin, first the neutrinos decouple. They are no longer in thermal equilibrium with the other electron, positron and photon. So, now we have the neutrinos separate and electron positron and photons, they are separate, they do not. So, these two interact with each other, neutrinos have decoupled. Okay. So, they are separate. Let me put it on a different slide now. So, I am just putting the overall scenario, and finally what happens is that again at around 10 to the power 10 Kelvin, the electron, which also corresponds to the mass scale of the electrons and the protons, if you convert the electron mass to temperature you will get something like that. So, the electron positron pairs, they annihilate at temperature of 10 to the power 10 Kelvin. Okay. So, a point I forgot to mention, to determine that the neutrinos have decoupled, you have to actually consider the reaction rates, just like a chemical reaction. Okay. These are reactions, the cross section is the weak interaction cross section. You have to consider the reaction rates, and if the reaction rate is slower than the expansion rate of the universe, then you can say that it has decoupled. Okay. So, the universe is expanding faster than the reaction is proceeding. So, the reaction has basically decoupled, it is ineffective in keeping the neutrinos in equilibrium. And then at a lower temperature, slightly lower temperature afterwards, the electrons and positrons, they annihilate again at a temperature of around 10 to the 10 Kelvin. So, after the electron positron annihilates, what happens is that during this annihilation process they are in equilibrium. So, they dump their energy into the photons. The photon energy is okay. So, they annihilate and they produce photons. So, here what you have is neutrinos which are decoupled, and you have the photons. Okay, this happens later. So, first the neutrinos decouple. Okay, so you have these three things. So, first let me go through over it again. This is the overall scenario. Initially at temperatures higher than 10 to the 10 Kelvin, all of these are in equilibrium. Okay, so you have the neutrinos, the electron positron pairs and the photons all in equilibrium. Then at temperatures of around 10 to the power 10 Kelvin, the neutrinos decouple. So, the neutrinos are separate, the electron positron pairs and photons are a separate fluid. These two are in equilibrium. And then at similar temperatures also, but subsequently the electron positrons also annihilate. This falls below the mass scale of these particles. So, they annihilate to produce photons. So, you are left with neutrinos and photons, and this continues till the present. Okay. So, this thing is what we see it, and we know that these are not interacting with each other. So, if they do not interact with each other, they will just, the temperature will just fall as. So, after this they will just expand freely, you can think of it like that. So, they move freely in the expanding universe. So, the temperature falls as 1 by A. So, once this electron positron pairs have annihilated, they just, the temperatures of these two things just fall as 1 by the scale factor. Okay. There is a certain amount of residual electrons which are still interacting, and the protons which are still interacting with the CMBR, but I have shown you that the heat capacity of that is very small, right. So, those interactions do not really affect the CMBR. The heat capacity is extremely small. Okay. So, after this we have already studied what happens. Okay. So, let us now consider this. Okay. So, let us work out the energy density in the neutrinos and the electron positron pairs. Okay. So, that is what we will do now. We have discussed this in the last class. Both of these I have already told you have zero chemical potential, that is what we are assuming. So, the number density of particles The number density of particles, this we had written in the last class, in general is given by this. This is the number density of particles with angular frequency omega in the solid angle d omega. We want the number density. So, this is the with number density in this angular frequency range, this solid angle range. We want the total number density. So, you integrate over the solid angle, that gives you 4 pi, right. So, and we will express this in terms not of the angular frequency, but of the momentum. For the particles that we are dealing with, it is more convenient, well, it does not really matter. So, we can as well express it like this. These are all relativistic particles. Okay. The temperatures, so we are dealing with a situation where the temperature is much higher than the rest mass of electron positron, otherwise they would not be there, they would have annihilated. The temperature also we are assuming is much higher than the rest mass of the neutrinos, if that is non-zero, and this obviously is relativistic. Okay, we have already worked out number density, energy density of this. So, now we want to work out the number density and energy density of the fermions. Okay, so so let us first write down dN. Oh, dN is already here, so we want to calculate the energy density of the fermions. Okay, energy density. This is, so let us do it for the neutrino first. So, we want to calculate the energy density of the neutrinos. So, we have to multiply this number density with h cross omega, because this is a number density multiplied by h cross omega. So, what we have is, just look at this, the solid angle integral gives us 4 pi. So, 4 pi into 2 gives us 8 pi. This will cancel out with a factor of 8 here. I have pi cube, so I have 1 by pi square left, c cube left outside. Okay. So, this is equal to 1 by pi square c cube then I am going to multiply this with h cross omega. I could also multiply this with h cross square and this with h cross. So, this then becomes, okay, let me just write it down and do the simplification, it will be easier. So, I have h cross omega and I have omega square d omega, and I then have to put in the occupation number, which we know for a fermion, it is exponential h cross omega, that is the energy, by kB T plus 1, right, that is for a fermion. For a boson it is minus 1. The chemical potential we have assumed to be 0. Okay, so again we can define h cross omega by kB T to be equal to y. So, with this definition, this becomes 1 by pi square c cube. So, we have to multiply this with h cross square and this with h cross, so that gives us h cross cube, which I have to divide with. So, divide by h cross cube then I have to multiply this whole thing, I have to divide this thing inside with kBt to the power 4 powers of that. So, I have to multiply this with kBt to the power 4, and I have the integral 0 to infinity y cube dy by e to the power y plus 1. We have already worked out exactly the same thing for the Bose-Einstein distribution, just that we had a minus sign over there. Okay, so for a Bose-Einstein distribution, if it were a minus sign, then I would have got some constant, the Stefan-Boltzmann constant, into t to the power 4. Okay. Now we have to evaluate the same thing except that there is a plus sign here. To do this, what we do is we utilize the identity that 1 by e to the power y minus 1 plus 1 by e to the power y plus 1. So, if I add these two, I have to multiply this with this factor and I have to multiply this with this factor, and then I can just add these two things. When I add these two things, rather it is not let me put it this way, it will be better if we, it is a minus sign here. So, this is equal to e to the power y plus 1, this whole thing no it was okay, sorry, this okay. So, this is equal to, I have to multiply this with e to the power y plus 1 and then minus e to the power y minus 1, the whole thing divided by e to the power 2y minus 1. This is equal to, then these two, these terms will cancel out. What I will have left is 2 by e to the power 2y minus 1, right. So, we have this identity. Now, we can use this identity, okay. How to use this identity? So, if I integrate, if I multiply by y cube, let me just look at this integral first. The first integral that I require is, or okay, this itself is not the one that we need. What we need is 1 by e to the power y minus 1 minus 2 e to the power 2y minus 1 is equal to 1 by e to the power y plus 1. Okay, so we have expressed e to the power 1 by e to the power y plus 1 in terms of these two integrals, which we already know. Okay, so now what we are going to do is we can multiply this with y cube and then do the integral. So, if we do that, let us just do it. So, the first one I will multiply with y cube dy e to the power y minus 1 0 to infinity minus 0 to infinity 2 y cube dy by e to the power 2y minus 1 is equal to the integral that we require, right. So, this is the integral that we require. Now, we already know this integral, we already know the expression for this integral, that is what we get for the bosons. Now, this integral can be easily converted to this. So, we just redefine the variable. So, if you just redefine the variable, what you have to do is you have to define in this integral, define 2y to be equal to x. So, then this becomes x cube dx. I have to then divide by 2 to the power 4. Dividing this by 2 to the power 4, there is already a factor of 2. So, I get 2 to the power 3. So, this is actually 1 minus 1/8 0 to infinity y cube dy e to the power y minus 1, the right hand side. This is equal to this. Okay, so what we see is that 0 to infinity y cube dy e to the power y plus 1 is equal to 7/8 0 to infinity y cube dy e to the power y minus 1. Right. So, the integral for both fermions is 7/8 of the integral for bosons. Okay. Similarly, let us also at the same time work out the integral that we get for when calculating the number density. So, when calculating the number density, there will be, instead of y cube, there will be y square. Let me just show you the expression and it will be clear. When calculating the number density, so this is in the integral here, we will not multiply by this factor h across omega. If I do not multiply by this, then I will get y square. Okay, so for number density, the integral that I require is y square into this, not y cube. So, if I have y square over here, then I have to multiply this. When I replace this variable 2y is equal to x, then I have to multiply this with 2, I have to divide it by 2 to the power 3. Here it was 2 to the power 4 because there is y to the power 4. So, I have to divide by 2 to the power 3, which is essentially dividing by 8, already a factor of 2. So, this gives me 3/4 instead of 7/8. Okay. So, for the number density, we also have this integral 0 to infinity y square dy okay. So, what is the consequence of this? The consequence of this is that the consequence of this finally is, let me come back here, the consequence of this is that the energy density of the neutrinos is 7/8 of what I would have for the bosons. Okay, so if they are at the same temperature, the energy density for neutrinos, one species of neutrinos which has two polarizations, one species of neutrinos would be 7/8 into the Stephen-Boltzmann constant e to the power 4. Okay. So, if the temperature were the same for both the neutrinos and the CMBR, then this would be exactly 7/8 times the energy density of the photons, if the temperature is the same. So, if I have neutrinos in equilibrium with radiation, then this is what happens. Okay. Similarly, the number density of neutrinos is 3/4 of the value for photons. Okay. So, if the temperature were the same, then this relation would be true. Now, the question is the temperature the same or is it different? Okay, that is the next question. What is the temperature of these neutrinos now or at any time? Okay. Now, let us go over this step by step again. So, at temperatures more than 10 to the 10 Kelvin, when the universe had temperature more than 10 to the 10 Kelvin, the temperatures, these were all in thermal equilibrium, the temperatures of these three were the same. Okay, fine. Now, with the expansion of the universe, sorry, this was the, with the expansion of the universe, the neutrinos decouple. Okay. Once the neutrinos decouple, the temperatures of the neutrino, the distribution function of the neutrino is frozen, it does not change because they do not interact, no neutrinos are produced, no neutrinos are destroyed, they do not interact with anything, okay. They are no longer in thermal equilibrium. So, once they decouple, the distribution function is frozen and it is just the same thermal distribution function which it's when it decoupled, the temperature just falls as 1 by A. Okay. So, after neutrinos decouple, T neutrino falls as 1 by A or proportional to 1 plus Z. Now, the electron, positron and photons, they are also in equilibrium and they also continue, the universe expands. So, the temperature of this also falls as 1 by A. Okay. So, T electron, which is equal to the positron also, and T gamma also scales as 1 plus Z. Fine. So, this is what happens, they have decoupled and again the expansion is continuing. So, they are both the same. This continues until the electron positron annihilate. Okay, once the electron positron annihilates, what happens is that this dumps the energy of the electron positron gets dumped into photons. So, the energy in the photons actually goes up because the electron positron pairs annihilate and all the energy in that goes into the photons. The neutrinos are decoupled, so they are not affected. Okay. So, the photon energy goes up in this process. So, the energy content in the photon goes up, that is the main thing. Okay. So, after this, the photon temperature has gone up compared to the neutrino temperature. Okay, let us calculate this. So, the conserved quantity is the entropy, right. So, the entropy is the conserved quantity because this is an adiabatic. The whole thing is adiabatic. So, entropy is conserved. Okay. So, let us say that the decoupling occurred at a temperature T. Okay. So, the decoupling at some temperature T. Now, before decoupling, what is the entropy? So, let us take a volume V and we have worked out the entropy of a photon fluid. We have worked this out. So, the entropy of the photon fluid we have worked out, it is 4/3 AB T to the power 4 divided by T, that we have worked this out in the last class. Okay. So, this is for the photon fluid and we also have a contribution from the electron positron pairs, and the electron has got 2 spins, the positron has got 2 spins, right. So, so there is a factor of 7/8. So, it is this 4/3 comes because d internal energy by T from there. Now, relative to this, the electron positron pair is going to have, there are 2, the electron and the positron, separately each of them have 2 spins. So, that will be a factor of 2 relative to this, and then for the electrons, the energy density we have just worked out, it is 7/8. So, the entropy is also going to be 7/8 AB, the Stefan Boltzmann constant, T to the power 3 cube. Okay. I am just simplifying this. So, this comes out to be 4/3 okay, 4/3 the Stephen-Boltzmann constant. This is before decoupling. Okay, so this is before decoupling. No, sorry, what do you mean by? Let us take this. Ignore this. Please ignore this thing which I had said. Let us take a temperature which is before annihilation, T. Okay. So before annihilation, this is what happens. So AB, and then I have 11 by 4, because 1 plus this is 7/4, so 11 by 4 into T cube. That is the entropy before annihilation. Okay, into the volume V. That the universe is expanding, so you have to keep track of the volume also. So this is the entropy before. Now after annihilation, the entropy is conserved, because this is in equilibrium, it is a reversible process, the entropy is conserved, but the electrons are no longer there, electron positron pair. So after annihilation, this has a temperature T prime, this has a volume V prime. So after annihilation, the entropy is going to be 4/3 AB T prime cube into V prime. Okay, and this is the temperature of the photon fluid. So I am showing a gamma here. Okay, temperature of the photons, CMBR temperature. Now let us, this is for the photons. Okay, photon and the electron positron pair. Now for the neutrinos, before annihilation at temperature T, volume V, that is before annihilation, the entropy, so there are n new species. Let us just take one species of neutrino. There are 3 different species, we believe, the electron neutrino, the mu neutrino, and the tau neutrino. Let us just take one of them. So for one of them, this is 4/3 into 7/8 into AB T to the power cube into V. Okay. Now after the annihilation, the neutrinos are not affected by this. So after annihilation, this is before. Now after annihilation, the neutrinos, this is going to be 4/3 7/8 the Stephen-Boltzmann constant, T neutrino to the power 3 volume, this is volume prime, oh sorry, this is volume prime, right. So the neutrino temperature at the same instant as this, we are denoting by T neutrino. Okay, so at this instant before annihilation, they both have the same temperature, the neutrino and the electron positron. Afterwards, it is obvious that the temperature of the photon has changed. Okay, so here the temperature of this and this is the same, because the neutrinos have decoupled. This continues to be in thermal equilibrium with each other, the electron positron. So they exactly evolve in the same way. After annihilation, the excess entropy, the energy has been dumped in, but the entropy between here and here is the same. So now what we would like to do is, we would like to determine the ratio of T neutrino by T photon from this. and this. Okay, so from here you can get the ratio of T photon to this T. From here you can get the ratio of T neutrino to this T. Okay. So from here, then from these two you can just eliminate this T over here, and what you will get is that this is equal to this factor 4 by 11 to the power of 1/3, right. This is a factor from here. Okay. And what this tells us is that the temperature of the neutrinos at present is equal to 1.95 Kelvin. It is lower. Okay, the temperature of the neutrinos is 1.595 Kelvin. It is lower than the CMBR temperature because the CMBR received this extra energy from the positron electron annihilation. Okay, after that they both just evolve as 1 by A as the universe expands. Okay, so if you extrapolate to the present day, this has a temperature 1.95. The number density of neutrinos for each species, again you can calculate the number density. So there will be this factor you can just work out. So I had told you that the number density is going to be a factor of 3/4 less to start with, and it is proportional to T cube. So there is this factor of 4 by 11 that is going to come in, right. And finally, so let me not work it out. So the temperature itself is lower, and the number density of neutrinos is, if the temperature is same, but the temperature also is lower. So putting in that factor, so that is a factor of 4 by 11, right, 1/3. The number density goes as, so this gives us 113 1 plus Z cube per cc. Okay, so this 4 by 11 comes because the temperature of this of the neutrino is lower than the temperature of the CMBR by this factor to the power 1/3. The number density is proportional to T to the power cube, so this factor comes over here, and this is because the number density of neutrinos is related to number density of photons at the same temperature by a factor of 3/4. Okay, so putting in both of these factors, what we get is the number density of neutrinos for one flavor is 113 1 plus Z cube per cc, per centimeter cube. Okay, so for photons, recollect, it was 420. For neutrinos it is 130. This is an important number. Okay. Let me give you a problem. Assume that problem, okay, so it's an interesting problem. Assume that neutrinos, let me just put it here. Assume that neutrinos have mass, one flavor of neutrino has mass m nu. Okay. So if this were true, then the neutrinos would be dark matter, because they don't interact. Neutrinos don't interact with, they only interact through the weak interaction. Okay, so they don't interact with electrons, protons. They're very weak, they interact only weakly. Okay, so with that too with nuclear particles. So these are dark matter. So they would be there, but you would not be aware. They would not emit light. Okay, so suppose these neutrinos were dark matter, then we know that the density of neutrinos, you can straight away calculate it from here, right. It would be the number density of neutrinos into the mass of each particle. The number density of neutrinos is fixed because we know that they were in thermal equilibrium in the past. You cannot change that. You can change that provided if you put in the chemical potential. Okay, then you can change the ratio of antineutrinos and neutrinos, but assuming that the chemical potential is 0, then the number density of neutrinos is fixed. Suppose they have a mass m nu, then you can just predict what the density of that neutrino component is, right. Now we do not want this density, so let us say that we say that okay, neutrinos have some mass and they are the dark matter, it is a possibility. Okay. So suppose now you do not want the density in these neutrinos to be much greater than the critical density of the universe. If the predicted density turns out to be much greater than the critical density, then the universe would have already collapsed. Right. If you have the actual density more than the critical density, the universe is going to be in a model that is going to collapse, right. And if it is too much higher, then it would have already collapsed. Okay. So if you or another way of putting it is, if you increase this, the age of the universe actually comes down. Okay. So the observed age of the universe puts limits on this. So let us assume you just want this to be equal to this. Okay, it cannot be more than this. Just let us just put this constraint. Then what is the restriction on the neutrino mass that you get from this? Okay, this gives you a constraint on the neutrino mass. And for many years these were the some of important, very important constraint on neutrino mass. Now there are better constraints from cosmology, okay, and from particle physics also, but at one time this criteria was a very important constraint on the neutrino mass. Okay, so one of the first people who pointed it out, it was in a paper by McClelland and Kaushik, Ramnath Kaushik, okay, Kaushik is an Indian astrophysicist. Okay. Now assuming, coming back to the standard picture where the neutrinos are relativistic particles, so assuming that the neutrinos are relativistic particles, they will make a contribution to the relativistic density of the universe. Okay. So we have already estimated what this contribution is for the photon fluid. Okay. So for the photon fluid we have done this estimate. So for the photon fluid we find that we have worked out what omega photon is, we have worked this out, and this is basically the Stephen-Boltzmann constant e to the power 4 divided by the critical density of the universe, where we have expressed this now the Stephen-Boltzmann constant in kg per meter cube, okay, instead of joules, kg per meter in terms of mass density by putting in appropriate powers of c square, and we have worked out this number. Okay. Now what happens when you put in neutrinos? Now so let us work out what happens when you put in neutrinos. So now the relativistic particles has contributions not only from the, it will be some factor 1 plus, so the neutrino energy density would be a factor of 7/8 less if the temperature of the neutrinos were the same as the temperature of the CMBR. But we also know that the temperature of the neutrino is lower by a factor of 4/11 to the power 1/3. So it is going to be, the energy density is going to be lower by a factor of 4/11 to the power of 4/3. Okay, and then we could have many species of neutrinos. So it is currently believed that this number of species is 3. There are the electron neutrino, the mu neutrino, and the tau neutrino, 3 kinds. Okay. So for 3 species of neutrinos, this number omega relativistic turns out to be 1.68 times omega gamma, and it has a value 4.22 into 10 to the power minus 5 H minus 2. Okay. So, this is the energy density, the density parameter for the relativistic particles in the universe, where we have also included the neutrino contribution. Okay. Now, the neutrinos, it may happen, could be massive. Now, whether you treat it as relativistic or not would depend on what the ratio, the mass value of the mass is. If the mass is much less than 1.95 Kelvin, then you could still treat it as a relativistic particle. If the mass were more, then you cannot treat it as a relativistic particle, it would be non-relativistic, and then you would it could act like dark matter. Okay. So, in the standard scenario, the neutrino is relativistic at present, and this is the contribution to the density of relativistic particles. Okay. So, the bottom line of this discussion was that in addition to the cosmic microwave background radiation, which is a thermal radiation that fills the whole universe, inside which we are embedded, we are sitting. So, it is there 420 particles per cc. There is also a thermal neutrino background, just like the thermal cosmic, the microwave background. This is a background of neutrinos which have a thermal distribution at a temperature which is slightly lower than the CMBR temperature. Now, detecting this thermal neutrino background is a very difficult issue, because the neutrinos are very weakly interacting particles. So, detecting neutrinos is extremely difficult, and this neutrino background has not been detected, and the prospects of detecting it are quite bleak in the near future. But this is an important thing that should be borne in mind, that in addition to the microwave background radiation, there is also this neutrino background inside which we are living. Okay. And this neutrino background, if it ever had mass, it has a lot of other implications also. Okay. If it does not have mass, then it is not all that very interesting. I mean, it really does not have very important cosmological implications. It does have implications, some implications, we shall come to this, but if the neutrinos were massive, then the cosmological scenario gets considerably modified, as I have pointed out, and I have left it as for you as an exercise to work out what the mass, what the restriction on the neutrino mass you arrive at from the, if you put in the requirement that the density of the neutrinos should not be more than the critical density of the universe. Okay. Now, very briefly, let me just remind you that in the last class I had given a problem, and this problem was that there is an observer moving with the velocity v. So, there is an observer here OR with respect to whom the CMBR is isotropic. So, this observer sees a thermal distribution. Now, there is another observer O, this is a rest observer, who is moving at a velocity v with respect to the CMBR, and I had asked you to work out the spectrum that this moving observer would see. Okay. Now, this problem is quite simple. Let me just indicate to you how to work it out. Now, the first thing is that in the rest frame of the observer who is at rest with respect to the for the observer who is at rest with respect to the CMBR, the occupation number n, we can write it as a function of nu. We know that this is 1 by exponential h nu by k t minus 1. Now, the occupation number, what is going to be the occupation number for the observer O? So, the occupation number of a photon of a particular mode we know is not going to change, because photons are not destroyed, neither destroyed nor created when I go from one frame of reference to another. Okay, I am seeing the same photon. All that happens is that the frequency of each photon is now different. And what is the relation between the frequency of the photon here and the frequency of the photon here? So, let us see. So, this observer is moving, let us say, with speed v like this, and let us say that he is observing at an angle theta. So, with respect to this frame, this observer is moving like this, and this observer is observing at an angle theta. Okay, this observer. Then the frequency of the photon in this frame of reference is going to be the frequency in the rest frame of the CMBR, and then there is going to be a Doppler factor, and the Doppler factor is 1 plus v cos theta by c. And v by c is extremely small. So, if I know nu, the observed frequency, I can predict what the corresponding frequency in the rest frame is, right. I can just invert this relation, v by c is very small. So, nu r is equal to nu 1 minus v by c cos theta, right. So, if I know nu, the observed frequency, I can predict what the frequency of the photon is in this frame. Now, I want to calculate the occupation number in this frame. That will be the occupation. So, I want to calculate in the observer's frame the occupation number of a particular photon. Let us call this nr, okay, in the rest frame. So, I can say that in the if I go to the rest frame, the frequency is going to be different. I just calculate the occupation number of that photon, that is going to be the occupation number of this photon with frequency nu in this frame of reference. Okay. Now, you can, from this you can work out what the occupation number in this moving frame is, and you will find that you can represent this in terms of a modified temperature that depends on the direction. Okay. So, please do this exercise. Let me stop over here.